Okay, good. So, welcome back. This last lecture of the course. So it's been quite short, but yeah, really intense. So 8 lectures in just a span of a week was quite heavy load. So also thank you for your patience to keep up with me. So. This morning we left with the idea of secret sharing, not secret sharing, garbled circuits. Let me see, I need to, take exactly the focus back on the right window. So, we said how to use garbled circuits in general to compute any Boolean circuit. So any Boolean function, and if we are able to implement the function that we want to, let's say, evaluate by using private inputs, so in a distributed setting where the users do not want to share their inputs to the other, then we can use this construction if we are able to, let's say, transform this function into a Boolean circuit. And it's, let's say, quite efficient in the sense that we only need oblivious transfer, that is the heaviest part, because we are using public key cryptography in that part, and public key cryptography is more computationally intensive than symmetric key cryptography. On the other hand, after the first layer, we can just limit ourselves to use the AES, for example, encryption, symmetric encryption algorithm, or any other symmetric encryption algorithm that we like and that is secure enough to evaluate the garbled circuits in each of the subsequent layers. So now we are going back a bit to secret sharing that we already introduced a couple of lectures ago. And so just to recall, if you remember, secret sharing is a protocol that is able to give the possibility to a dealer, to a central party, to share a secret information among a set of n players in such a way that, for example, in the threshold secret sharing setup, we need at least k out of n players to recombine their shares to reconstruct the original secret. Otherwise, less than k shares are not able to gain any information on the value of the secret. And this is exemplified by this picture here, where you see like we have 3 players and we want to make a threshold secret sharing scheme 2 out of 3. So at least 2 players need to combine their shares in order to reconstruct the secret. So the dealer will start with the secret information that is represented by this key here, because usually the secret is a cryptographic key. And it will generate these 3 shares, B1, B2, and B3. Okay. And then these will be securely transmitted to the participants P1, P2, and P3. Then at a later stage, we will have any 2 combinations of players, so P1 and P2, P2 and P3, and then P1 and P3, that can combine their respective shares in order to reconstruct the original secret. And yeah, we noticed that if we use certain combinatorial structures, such as, for example, Latin squares, so a simple Latin square is basically a 2 out of 2 secret sharing scheme, because we can basically share a single secret, so a number between 1 and n, where n is the side of our Latin square. And then we will use the row coordinate and the column coordinate as the shares to give to let's say, to 2 players like Alice and Bob, and then they need to combine together the row and the column in order to uniquely identify the entries that the dealer meant to share with them. On the other hand, if they try to do that alone on their own, they won't have any possibility to learn anything about the secret, because they will see either on the row or on the column or all numbers going from 1 to n, and everything is equally likely. So, like we said, there are Latin squares for 2 out of 2 secret sharing, threshold secret sharing. And we saw that in the general case, we can use, for example, mutually orthogonal Latin squares to construct 2 out of n secret sharing schemes. Or otherwise, in the more general case, we use orthogonal arrays, where we can use, let's say, the last column of the array, like this one, as the column that is devoted to the secret. So the dealer will choose if the secret is, for example, 2, let's say, he will select randomly one of the rows that is containing 2 in the, well, sorry, these are 3 because it is a 4x9 orthogonal array. So we have 3 possible secrets in total. So it will find in one of the 3 rows that are containing 2, what are the corresponding shares that are the entries in the other columns, and then it will distribute these shares to the participants. If the participants, in this example, we still have actually threshold equal to 2. So if 2 participants wants to combine their shares, so by the strength of the orthogonal array, which is 2 in this case, they can say, okay, we know that there is exactly 1 row in this subset of columns, for example, the first and the third one, where we get, for example, 2 and 1 as shares for the first and the third player. And so we know that the secret is this one because the orthogonal array is assumed to be public. This is okay, but in practice, how do we construct one of these orthogonal arrays? Because if we have something that is very, very big, like we want to share a secret key of 128 bits, then you can see that it is a problem to have the whole Latin square or the whole orthogonal array to share these. Maybe we don't even have enough memory again in the whole universe because it's such a huge number that we don't have enough atoms to represent these huge tables. So in practice, what we want to come up with is an algorithm that is able to say, okay, I give to you an input like the initial secret, and that is, let's say, a compact representation such as an AES key, encryption key of 128 bits. And then from there, you give me also like an input, for example, some random numbers, some randomization. And then from there, I will tell you what are the respective shares to distribute to the players. The idea is that this algorithm is going to sample using those random numbers one row in the orthogonal array, but it doesn't need to have the whole table, so it can compute it in an implicit way, in a certain sense. And the most basic way to do this, if we are restricting ourselves, and luckily this will be the case for private machine learning, so we have the very restrictive case of n out of n secret sharing scheme, so we need all possible shares from all participants in order to reconstruct the secret. So even if we are missing one, then we are not able to find any information or to gain any information about the value of the secret. So in this case, we can assume, for example, that the secret is a number from 0 up to n-1, so it is a member of the residue class ring Zn. And then the dealer will find a random sum that when reduced modulo n, big N, it will give us the secret S. So this means that this sum, in particular B1, B2, Bn, the single summons, will be the shares to be distributed to the players. And the idea here is again quite simple because maybe, oops, I did something stupid. Yeah. Let me go back here. Yes.
A reminder theorem, something like that.
A reminder? What?
Chinese theorem.
Yes, one of the possibilities is to use the Chinese remainder theorem. Here it is even simpler in a certain sense, but you can also use that. Yeah. Chinese remainder theorem is one of the ways to implement secret sharing schemes. But actually here what we are doing is that if you take, again, n equal to 2, so you will find out that you want to have a reconstruction phase where the secret is equal to B1 plus B2 modulo big N, okay? And now again, just for the sake of example, let's say that n is just 4. Mm-hmm. So we will have our residue class ring that is Zn, so 0, 1, 2, 3. And then we are considering the sum operation in this reconstruction here, so sum modulo n. So if you are going to draw the Cayley table of this operation, of this binary operation, what we will get is a 4x4 square, where we will have the numbers from 0 to 3 in this case, because we are living in this set here. And this will be, let's say, the first summand, so B1. This will be the second summand, so B2. So we will have here, let's say this is devoted to, let's write it here. So this is the row of 0 for B1, the row of 1 for B1, the row of 2 for B1, and the row of 3 for B1. And here for B2, we will have the column for 0, the column for 1, the column for 2, and the column for 3. And then from here, what we are doing is simply to say, okay, if we have B1 equal to, I don't know, 1, for example, and B2 equal to 3, then I need to go on the second row and last column, and this will be the value of the secret. So this will be S. And this, even if you have, for example, 2 and 2, then it will be the same thing, because you're basically computing a sum modulo 4 in this case. So you're always moving inside the D square. So the case of n equal to 2 players with this additive secret sharing that we have just introduced is simply again the case of a Latin square, where in particular the numbers are done in this, are filled in this way in the square. So here we will have 0, 1, 2, 3, because we are summing 0 to all with all possible numbers here on the columns. Here we are summing 1, so we will have 1, 2, 3, 0. And then we will continue. This is again the same Latin square that we saw a couple of lectures ago, where we are doing a cyclic shift of the rows. So we will have 2, 3, 0, 1, and finally 3, 0, 1, and 2. So if the secret was 2 and the dealer is going to find these 2 coordinates for the Latin square, then he will give 3 to the second player, B2, and oops, sorry, I did a mistake. Okay, it was 3 for the second player and 3 for the first player as well, because we are going to use this column and this row. I was looking at the other way around before when I was talking and saying that it was 1. Okay, so using this formula here, we don't need to have the whole specification of the table. This is just the extension of definition of this operation here. This is the intentional, let's call it like that. And if we have n that is larger than 2, it will be the same. The only difference would be that we will have some kind of hypercube, something like this, where each slice basically would be a Latin square, and then it will become like an hypercube in if we have a dimension larger than 3, but the idea is always the same. Like we are taking all n dimensions of this hypercube, and then we are summing them, and the sum of these coordinates modulo n will be the value of the secret that is located in a particular place on the hypercube. So this is quite simple to let's say implement n out of n secret sharing scheme, and this is usually called additive secret sharing scheme. Okay, let's continue. So now we do, let's say, a quick close-up about how to use this secure multi-party computation for private machine learning, in particular using additive secret sharing. Okay, it is, yeah. So the importance of privacy in machine learning is that when you look at the models that you are training, usually the source of data is at the edge, let's say, of a particular network. So you are generating data with your, I don't know, your behavior on your smartphone, like when you're browsing over internet, or on social networks, then your data are used to train like a particular, for example, reinforcement learning model to recommend you what is the next video to watch on YouTube, or the next post to visualize over Facebook or Twitter. And so the data are usually generated on edge devices like smartphones or cameras or other IoT devices. And these data, of course, produce better models, smarter models. What is the problem? The problem is that when we have a sharing of this data between these edges devices like smartphones and so on, with a central server that is like collecting this data in order to train the model and then give you like the inference later, then we might incur, of course, in privacy issues, because maybe we are revealing something about our behavior that we do not wish to share with others, especially with servers that are handled by big corporations, for example. And so the idea is that, okay, this is blocked. I will use, okay, let's see if yeah. It is just a bit stuck. Okay, now try it again. So this is the, let's say, general problem of collaborative learning. So in general, we want to train some machine learning models in a decentralized setting, in a distributed computing environment, where we are using, for instance, the data collected from several smartphones that are using a particular product. One such example is the Google keyboard. When you're using the Google keyboard, for example, on WhatsApp, you will see that while you're writing, it is suggesting to you what is the next word. So this next word is predicted by using a machine learning model that is collecting, let's say, the inputs of all other users that are employing this Google keyboard. So it learns, let's say, what is the next most probable word to complete your message by gathering all this data from other users. But of course, there is a privacy issue, because one does not want to give all these private messages on WhatsApp or whatever to Google, for example. So how do we cope with this situation? Well, one idea is called federated learning. And in federated learning, the idea is that we are able to train machine learning models, but without doing an explicit data sharing of the data from the edge devices. So each device, in this case, instead of having a single server, a single central server that is like giving a huge model over all possible input data, we will have a situation where each device or each client trains a small model locally, okay? So without sharing any information with the others. Then what you will share, this client, won't be the data that is used to train this local model, but the model itself. So the weights of the neural network, for example, that is trained. And after this model is shared over this central server. And this central server, what it does is simply to aggregate the values of all these models. So it will compute the prediction of all the single models that have been trained on a particular input, such as you have, beginning of a sentence, for example, and you want to predict what is the next one. So it will compute over all these local models, of which it doesn't know the original data where it was trained on. It will aggregate this prediction, and then it will do an averaging, fundamentally, of these models. And then it will give back the results. And this process, of course, is repeated in an iterative way. The idea, so this is, let's say, the federated averaging algorithm more in detail. So the idea is that until we converge to, let's say, a stable prediction for our model, the server is going to select a random subset of clients, so n clients in total, and then it will send the current parameters of the model that it gathered from the various local clients to each client in this subset. And then for each of these clients, it will say, okay, you are going to train this model over this particular set of data of parameters that I gathered until this time t. and get the corresponding model at time t plus 1. And then it will return the difference between the, let's say, models from the new time step t plus 1 and t. And finally, it will compute the aggregation of all these models by computing basically the average, the arithmetic mean of all these parameters. So the idea is that this is nice in theory, but they showed that it can have some problems. And the problem is that if it is done in this way, then the clients can learn some of the private information from the models, from the averaged model. Let me see if I can find, yeah, quickly these notes. Okay, so is here. So here now I'm just giving you a general idea of how it is working, and then we will move to the wrap up to keep it short. So where is the chalk? So the idea is that we have our central server, let's say, and then we have, for example, Alice, Bob, and Charlie, who are connected to this central server. So these are the 3 clients in this simple example. So the straightforward solution that is not even used by federated learning is that they send over this, so in this direction, their own private data. But of course, and this is the same also for the other 2, of course this is not good, because then you need to trust the server, that the server is a trusted third party. So this is not a good idea. So better, what is doing federated learning is to say, instead of giving directly the data, we'll give like an ML model. A machine learning model here, a local machine learning model here, and a local machine learning model here. So this would be, and of course we don't have just a single direction, but it is kind of an exchange, because if you remember the federated averaging, it is continuously updating these new models and sending them back to the clients. So what we want to do, the goal that we want to achieve, is to find the average, basically, which means that we can just simply think of it as the sum, because the average means just doing the sum of these models, and then we are normalizing by the number of clients that we have inside our subset. So in this case, we are going to use, let's say, basically a combination of secret sharing, and also there are some other refinements, for example, using Diffie-Hellman key exchange. Well, not exactly the Diffie-Hellman key exchange, but the discrete logarithm problem. So it is using the exponentiation, modular exponentiation, and then saying, okay, if I have like a known generator and a secret value for the exponent, then it is very difficult to retrieve the secret value in the exponent by just knowing the generator and the modulo for the reduction. So the idea with secret sharing at this point, for example, by using additive secret sharing, would be that, so the goal here would be to find if we have private inputs MA and MB and MC, then it would be to find the sum, so MA plus MB plus MC. And again, these messages now, what they will be the local prediction, let's say, from the local models, and then we want to aggregate them at the level of the server. And the idea then is that you use this, and you assume that this is a secret to be shared using secret sharing, so using additive secret sharing. So this will mean that we will have, let's say, using additive secret sharing, something like MA, which will be split into 3 parts. So again, using the, well, I already erased it, but the idea is that we are going to find like 3 splits for each of these. So we will also have for these messages here and MC here, and we will have, I don't know, let's call it MAA plus MAB plus MAC. And similar will be here by changing the subscripts. The idea is that once you have split the secret the private prediction, or let's say the prediction from this model local, in this way you will have 9 shares in total, and after that, by summing them up, the server is able to cancel all the other the intermediate shares, let's say, and retrieve the original sum, but not the original messages here. So this is the general idea. And okay.